Good afternoon. Shortly, we will hear an interesting lecture by Mr. Costa Gurgov on computer vision optics from photons to digital image. This is part of webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within Engineering Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in photonics and to encourage cooperation both within Israel and with photonics entities in the world. We are open to your ideas and would love to help foster new local and international collaborations. We are holding weekly webinars on various photonics topics. We will soon begin a series of webinars dealing with physics and quantum technologies for engineers. We invite you to sign up to follow the activity we would hold, which are published in our monthly newsletter. Per your request, the newsletter will deliver to you to your mail. My name is Shlomo Glaser. I am the manager of Photonics Israel. Mr. Gurkov, holding MSc in physics, is an optical system and lens designer with 15 years of experience in numerous fields, especially on vision and 3D imaging in consumer electronics devices. Mr. Gurkov is the CTO at Engage Photonics Limited, which develop integrated photonics devices. Mr. Gurkov, the floor is yours.
Yeah, all right. So I believe I'm live. Thank you very much, Shlomo, for the introduction. And I'd like to thank Photonics Israel for arranging this webinar. So this webinar is about computer vision optics. It's about designing the optics correctly to get the best possible image for your computer vision applications. So the computer vision world is rapidly evolving, and since the invention of processors and image sensors, even more so in recent years with the developments in machine learning and AI, processing images and obtaining information brings humanity and the world great benefits. It gives us the power to do things better, from medicine to agriculture, mapping, construction, security, production, and many other applications. Computer vision is the acquisition and processing of digital images. We want to deduce useful information about objects in the real world. It can be cell counting and morphology analysis in cytometry. It can be finding defects in the production line, localization and mapping for autonomous platforms like robots or vehicles, or utilizing multispectral satellite imagery to make agricultural decisions. So to the basics, to start things off, we will look at the physical components of the camera. There is the lens and the image sensor, the most important parts. The image sensor is typically mounted on some PCB substrate. To control the image sensor, commonly there is an ISP or some other kind of DSP chip on the same board or a separate board. Some kind of optical filter is present in the majority of cameras, commonly between the lens and the image sensor. Not shown is the camera enclosure, which holds everything together. Another component is the optical window, usually mounted into the host system's enclosure. It's not part of the camera, but it has a great effect on its optical function. Designing the digital camera correctly can mean the difference between success and failure of a project. You can optimize illumination and optical filters to enhance contrast of important material constituents. You can select the image sensor model, and you can select the f-stop value to be able to resolve critical object details. You can configure exposure time, pixel size, scan speed, and camera field of view to maximize an inspection system's throughput. The basic processes of computer vision are imaging, sensing, and processing. Today's presentation deals with optical imaging and image sensing, which can be defined together as digital imaging. To explain different concepts, we will be looking into some very simple examples. So to create a digital image, we first create an optical image at the surface of the camera's image sensor. An optical image is a distribution of light which resembles the object as it is viewed by the camera. The distance between the camera and the object is called working distance or object distance. It is critical to understand the process of optical image forming. So let's dive into the details. So we'll use some very simple diagrams, but it will help you understand the different trade-offs of camera design. Imagine a plane where we have an object comprised of a red sphere and a blue one. Suppose that we want to create an image of them at plane B here. And that means we want to get a similar distribution of light at that plane as the projection of plane A along the optical axis. So the way that these two objects are viewed along the optical axis is the same distribution of light we want to create at plane B. That means we want to get some red light incident right here and some blue light incident right here. And if I place a piece of paper at plane B, and I look at it, I would see an image which is similar to what's happening at this plane. So again, what happens is that typically some light is incident on the two objects, and the light contains a certain distribution of electromagnetic spectrum. And once these photons hit the red object, they are scattered all over. Different objects have different scattering properties, and we're not getting into that now. But all incident photons, the whole spectrum is scattered from the red sphere? Not exactly. Mostly the red wavelength photons. That's why the sphere appears red to us. So we have some red photons flying around from the red sphere. And so we need to bend those photons towards this area here. So we know that what bends light is a prism. So we place this kind of a prism in the middle, and we see the light bending inwards, and we get some kind of a blurry hotspot in the center. That's not much of an image, but we're getting somewhere. So the prism has a uniform bending power along the prism, but we see that at the top, we need to bend the light rays much stronger than at the center. So what we need is a variable power prism. And what does that is actually a lens. You see that the curvature at the center is weaker, and the angle of refraction, the curvature at the top, is stronger. That's why the rays over here bend stronger and towards the image. So what we get now is that you have something resembling the red spot and something resembling the blue spot at the image plane. So what you see here is that due to the path of light rays through the lens, the blue object is below the red object. So the image is always flipped relative to the object. Now, in this kind of symmetrical arrangement, we see that the object is the same size as the image, but typically we want to get a very small image because image sensors are small and we want compact cameras. So to obtain that, we position the lens much closer to the image plane, and we use a lens with a different focal length. The lens is now positioned at the distance S prime from the image, and the relation between the different distances and the focal length is shown here. The image is a scaled down version of the object, and the magnification by simple geometry is the ratio of distances. And so is magnification is the ratio of the image size to the object size. It's all very nice, but in practice, we cannot use a single piece of convex glass in real applications. The reason is that bending of all the rays at all wavelengths from the red object and the blue object to the image points is just too much constraints for a simple piece of glass. And to get a high quality lens, you need much more than a single lens. So if we look closely at the light rays passing through the single lens, we can see an example how a single lens with spherical surfaces will not be enough to get a sharp image. Rays from an on-axis object coming from afar will be hitting the lens at different heights, and we expect them to converge nicely into a very sharp spot, the image of the axial object. But if we check the rays from these areas, we can see that they converge steeper and they miss the image position. And this is called the spherical aberration. Similarly, for rays off axis, for objects off axis, we will get different aberrations like astigmatism and coma, and we will see that the image isn't so great for off axis imaging either. So without going deeper into that, if we reduce the size or the diameter of the lens, we can see that by giving up some of the light, we can actually get a sharper image. This is called stopping down the lens, changing the F number of the lens. And this way we control the aberrations of the lens, and we can get a sharper image. At this point, it is important to take a look at two important quantities, the focal length and the lens diameter D. The ratio F divided by D is the lens F number. And this is a very useful quantity. Note that when we stop down the lens, we collect less light and the imager is darker. However, in most cases, there will be less aberrations and the image can become sharper. So what the lens designer does is that he combines different lens materials and shapes and makes them compensate each other for aberrations, so that eventually the light rays behave well and give a sharp image. If, for example, you add an optical filter between the lens and the image sensor, it will break that balance sometimes and image quality will be degraded. The lens designer uses special optical design software to calculate and optimize the inner components of the lens assembly in a practical and manufacturable way to reach the required properties of the lens. There are many dozens of constraints that the optical designer takes into account. Different lens sizes exist for different image sensors and applications, and for each one, different approaches are used for assembling lens objectives, as well as different glass and optical polymer materials. An autofocus lens means it has a mechanism, a feedback controller, and a built-in algorithm which automatically brings the lens into focus. And we'll see an example in this presentation. A fixed focus lens does not have that feature. A zoom lens can change its focal length, typically by displacing some optical components inside the barrel along the optical axis. And therefore, it enables changing the field of view and magnification. Lenses have dozens of different merits, properties, and parameters, and to get a good image, they need to be considered. As we will learn in the practical example section, each application requires specific properties and relaxes others. It is important to understand the following points. The focal length of a lens is a geometrical parameter. It is not a physical length related to lens position. The point of geometrical projection, or the pinhole used in computer vision books, is at the center of the entrance pupil of the lens. Typically, it's a virtual point somewhere inside the lens. If you need to locate it for your application, consult an optics expert or a lens supplier. Focusing a lens is adjusting lens position to the right distance from the image sensor, and we will talk about that in detail. While at field of view center, the ray cone converges normally towards the image. In the off-axis situation, it is not so. The ray that goes through the cone center is called the chief ray. And due to some constraints, its angle relative to the optical axis can reach above 30 degrees for some lenses. We're talking about this angle here. And that can be a concern for some applications, and we will talk about that later. Following the simple geometry of first-order optics, for an object at angle theta from the optical axis, the image would be at distance y times f tangents theta from the image center. However, almost all lenses distort the image to some extent, meaning that they behave differently from that law. There are different reasons for that. The major one is that it is very difficult to design sharp imaging lenses which follow this geometrical law precisely. Relaxing this requirement and allowing some distortion often enables an optical designer to provide a better image. However, in some cases, distortion is unavoidable. For instance, if I want to have a camera with a 180-degree field of view, and there are such cameras, for a distortionless camera, the image sensor size would be infinite. You can see it here. For a 90-degree angle, the tangents theta is infinity, and you would need an infinite image sensor to accommodate this kind of field of view. So therefore, we must depart from that law considerably and map the 0 to 90 degrees to a finite image sensor size. In presence of distortion, rectilinear objects lose their shape, and the image exhibits barrel-type distortion. So if you photograph a grid or a building, this is the shape that you would see, this distortion here. After image acquisition, the image can be digitally corrected, compromising resolution. A special category of lenses is low distortion lenses, which are designed to provide somewhere between the fisheye distortion and the no distortion case. So you should consult an optical expert to find an optimal solution. So due to a number of reasons, a lens collects less light from an off-axis object. You can see here that this cone of light over here is much larger than the cone of light for an off-axis object in this example. For a thin lens approximation, lens shading goes as the fourth power of the object angle cosine. So this is the object angle, and the fourth power of the angle cosine is the intensity degradation for an off-axis object. This is the general expression for lens shading. However, that's just a first-order approximation, and the actual lens shading depends on additional parameters inside the lens and its matching to the image sensor. So in some badly designed lenses, the light beam gets truncated on internal lens edges, which causes another contribution to lens shading, and that is called vignetting. Lens with low f number collects more light and can have higher aberrations. However, it also has lower depth of focus, since the blur spot is much higher for a defocused image sensor. So this represents the position of the image sensor for two imagers. This imager has a high f number, smaller cone, and this image sensor, this imager has a lower f number, a much wider cone of light incoming at the image sensor. So you can see that if the image sensor is defocused to this position, then you can see here the blur spot is much smaller for the high f number lens than the low f number lens. You can also remember that the image shifts as function of object position. So therefore, if the object is located at a closer to the camera or further away from the camera, the image is focused before the image sensor or after the image sensor, and the blurring effect is different equivalently for the two kinds of imagers. And that's why you can get a different depth of focus for an imager with a higher or low f number. And that is something to really think hard about when you design your camera, because the f number has an effect on so many different performance aspects of the lens that the simple quantity is very critical. So from linear systems theory, we are familiar with convolution and linear space invariant systems. I'd like to talk about image sharpness in a different terminology, which is very important for computer vision algorithmicians. An imaging lens can be viewed as a space variant linear system. It means that blur, image, or image degradation is applied by the lens in a linear fashion. However, the blur kernel is not uniform across the image. The kernel is called the point spread function, or PSF. In spatial frequency domain, the MTF, modulation transfer function, is the quantity we need to know. Lens MTF for incoherent imaging for perfect lenses without aberration is an almost linear function, and there is a certain cutoff frequency right here. This is the frequency axis, spatial frequency. This cutoff is inversely proportional to wavelength and lens f number. It has to do with light physics. Again, since a lens is not space invariant, MTF is different for different regions in the image. Now, for a real lens, which has aberrations, the MTF will always be lower than a diffraction limited MTF. MTF is an informative and simple merit of image quality. However, the factors that influence it are very numerous and complex. Lens resolution is just the starting point, from which every added component like image sensor, optical window, filter, assembly accuracy reduces the resolution. It is the job of the optical designer to make sure that the lens delivers the required resolution together with all factors taken into account. So the optical image is a continuous distribution of light, and it is sampled by discrete pixels. One object point may have its rays concentrated nicely into a pixel. Another one may not be so lucky, and its energy would spread across neighboring pixels. To improve the light coupling into the pixels and compensate for chief ray angle, there is an array of micro lenses above the pixels, which is the micro lenses is part of the image sensor. To generate color images, there is also a color filter array below the micro lenses. Some image sensors are backside illuminated, meaning that the sensor chip faces the lens with the silicon side, and so there is less scattering and blocking. And that kind of sensors have higher sensitivity and better SNR. If we calculate the transmission function of a discrete sample and hold function, we will get a sync function. So the image sensor has its own MTF, and the overall system MTF can be approximated as the product of the two. Besides sampling, another factor that influences image sensor MTF is diffraction. The smaller the pixel and the longer the wavelength, the lower is the MTF of the image sensor. There is no point in designing an NAR imager with 1 micron pixels. There will be no image. So for those of you who survived this far, there is a small bonus. You can measure MTF of your camera very easily by using our free tool at our website. You simply take an image of a target, of a slant edge target, and you upload the image at our website, and you will get the camera MTF. So try out this tool at our website, follow the instructions on that page. So let's talk about image sensor noise. Photons are absorbed in the semiconductor, and the percentage of incident photons is absorbed is wavelength dependent and is called quantum efficiency, or QE. Upon absorption, an electron-hole pair is generated, and the charge is accumulated and stored in the pixel until readout. The image sensor accumulates the signal charge during the exposure time that is set in the image sensor. Image sensors carry out the exposure differently. Global shutter MTF, global shutter, CMOS sensor, and CCDs expose the whole array simultaneously, while rolling shutter CMOS image sensors apply a different scheme. We don't have the time to talk about everything, but while the pixels are being read out, image sensors employ different approaches to prevent incident photons from generating unwanted signal. In general, CCD image sensors are more expensive, they exhibit superior uniformity and noise characteristics, and they are mostly used for large format, high-end applications. In CMOS image sensors, each pixel contains a pre-amplification circuit with a few transistors. Image sensors enable electronic amplification of the signal, called analog gain. So about the gain factors and noise in signal generation, the amount of light the camera can receive during exposure is limited, first and foremost, by the full well capacity of the sensor pixels. It can be from just a few thousand electrons for smaller pixels to tens of thousands of electrons for larger CCD pixels. The signal is converted into voltage, and after analog gain, it is digitized. So a pixel can saturate due to a number of reasons. It can reach the maximum number of electrons, can reach the maximal voltage value, or maximal digital level. it is important to control the image sensor in real time, especially the exposure time and analog gain. The rule of thumb is that you need to allow maximal permissible exposure time without causing motion blur. And if the image is too dark, apply analog gain. Digital gain has little effect both in SNR. It has zero effect for SNR, and it has a little effect for computer vision applications. So a saturated signal is useless. Therefore, the image sensor exposure time and gain are controlled in real time to get optimal amount of signal over the frame. So typically, ISP chips analyze the statistics over the image in real time, and they correct different settings of the image sensor. The histogram is a useful tool to analyze that. Sometimes the scene's dynamic range is very wide, and we want to be able to distinguish between different light levels without having to use a 20-bit image sensor, which is very expensive, and the data throughput would be very high. So by redistributing the full range in a nonlinear fashion, we can achieve that. There are several, and that is called HDR. There are several techniques for HDR, and one of them is taking a few temporal exposures per frame. This is the exposure 1, exposure 2, and instead of a linear response, you get this kind of response for a pixel, and that, of course, covers a much wider range of possible exposure values. Actually, the correct drawing would be like so, like that, and like that. And so you can span a wider exposure range. Another technique for HDR is what Fujifilm had done. They incorporated a larger pixel and a smaller pixel in their array that they called Super CCD. So the main types of noise are FPN and temporal noise. FPN type is fixed pattern noise. FPN is characteristic to CMOS due to the difference in circuit properties of the individual pixels and circuit branches. DSNU is the difference in static offsets of the pixels, and PRNU is the difference between pixel gain. Shot noise is always present and is more dominant at high signals. This image demonstrates the nature of an image created by random discrete photons as function of exposure. It is clear how much better the SNR gets with higher exposure. The shot noise goes as the square root of the number of electrons incident. Yes, it doesn't settle with the units, but it is so. So the SNR is overall goes as the signal, the square root of the signal. So quantization noise is an important factor to take into account when considering the amount of digital levels that are utilized in practice in your application. For example, in thermal imaging applications, the image sensor can be 12-bit or 14-bit. However, often the environment's temperature is very close to object temperature, so the actual number of utilized digital levels is very small. Here we can see a typical report that we did of a camera noise test. The PRNU is typically 1 to 1.5%. The difference here is because of RGB filters. 1 to 1% PRNU is typical to CMOS image sensors. Temporal noise squared is extremely linear, and the reason is shot noise, as we mentioned before. we can see the dark noise here, and we can calculate the dynamic range from this value, and we can also calculate the SNR max, which is the SNR at the maximum possible signal. So about color perception and color imaging. Color is a characteristic of light that originates from human perception of light, and it is only relevant to human vision. The human eye has 4 types of photosensitive molecules, RGB cones and monochrome rods for low light conditions. Each of the RGB sensitivity curves is given by the CIE standards. To be able to acquire a color image, a color filter array is applied onto the image sensor by the manufacturer, making a periodic mosaic pattern of pixels sensitive primarily to red, green, and blue wavelengths. So you can see the spectral sensitivities or transmission of these filters. Once the image is acquired, the DSP interpolates each of the 3 sets of pixels into 3 images, same size as the original matrix. And so the RGB image is actually 3 images. Obviously, sampling each image at half the resolution reduces the effective MTF of the system considerably. There are standard means of determining camera color correctness, but one should never forget that everything begins with the light source. Therefore, the result will always depend on light source spectrum. Standard light sources and color test charts exist for such measurements. So let's take a look at a couple of practical examples of computer vision applications and how the optics was optimized for the suitable geometry or resolution requirements of those systems. So this is the Telecentric Imager. For a Telecentric Imager, unlike traditional lenses, which look at objects from a certain point of the pinhole of the camera, the Telecentric Imager is just as large as its field of view, and it looks at objects just orthogonally. And why do we need that? If you look at 3D objects with a traditional camera, you would see results like that. So if we want a metrologic precise camera which can measure quantities, but it would see nearby objects exactly the same size as objects that are further away, you need a camera like that, an object-based telecentric lens. And then it would see such objects in this way, as shown here. So this is the Telecentric Imager. Another interesting example is the smartphone autofocus camera. So this is a marvel of optomechanics. Really, the lens is suspended on a magnetic voice coil actuator, which can move the lens in a very precise manner back and forth in a closed loop control with image, and the lens position is actively controlled to provide an image that is always sharp. So the lens here is also very compact and made of aspheric, mostly plastic components made by injection molding, and it's a wonderful construction. And probably you've heard about some new developments in relatively new developments in Israel, which employ a folded architecture with some moving components inside, which was miniaturized to fit into smartphones. So I hope you enjoyed this presentation.